Having considered both the natural and the step response for the parallel connected RLC circuit, and also having looked at the natural response of the series RLC circuit, we have the fourth of four configurations that we need to consider, and that is the step response of the series connected RLC circuit. As we did in the past, the step response refers to the response of the circuit when a source of power is suddenly applied to the circuit. In this case, we'll have this voltage source, V sub S, applied to the circuit here. And from just an intuitive sense, we know that as this closes, we can't instantaneously change the current in the inductor. And so it will gradually change. As it begins to grow, the voltage across the capacitor is going to grow. And the voltage across the capacitor will continue to grow until it stabilizes at some voltage, in which case it becomes an open circuit. And that open circuit will allow no further current to flow. So in the case of the series connection, the capacitor ultimately will have a charge on it. There will be no current flowing through it, and so there will be no final current in the inductor, no final voltage or current associated with the resistor. Once again, we need to write a differential equation to describe the dynamic of this circuit. To do so, once again, we're going to be writing a Kirchhoff voltage loop around this circuit, where we're going to be summing the voltages, plus to minus V sub L, plus to minus V sub R, plus to minus V sub C. And I should say that the assumption on this derivation is that there is no initial energy in the circuit. It turns out that it doesn't matter whether it's there or not. When we get done, we'll be finding constants based upon the initial conditions of the circuit. So here we have I defined. We're going to, for reasons that become obvious here in just a second, rather than writing the equation in terms of I, we're going to write it in terms of the voltage across the capacitor. And we're going to note that I, the current that's flowing through this series, is the same in each one of these devices. So the current that flows through here is going to be the same as the current in the capacitor, which we know to be equal to C times the derivative of the voltage across the capacitor with respect to time. Now, the voltage across the inductor is equal to L times di dt. Well, I is that, so di is going to be the second derivative of that, or the voltage across the inductor is going to equal L times C times the second derivative of the voltage across the capacitor with respect to time. The voltage across the inductor, the voltage across the resistor is just going to equal R times I, or R times C times the derivative of the voltage across the capacitor. And finally, the voltage across the capacitor is just the voltage across the capacitor that we're writing in terms of. And so now let's go ahead and write a voltage loop equation around that circuit in terms of these. So V sub L, starting right here, plus to minus V sub L is equal to L times C times the second derivative of the voltage across the capacitor with respect to time, plus V sub R, which is R times C dV sub C dt, plus V sub C must equal then the source voltage V sub S. Now if we divide both sides of the equation by LC, we get then the second derivative of the voltage, plus dividing this by LC, the C's cancel, and we get R over L times dV dt, plus 1 over LC times V sub C is equal to V sub S over LC. And once again, we have a second order differential equation, constant coefficients. It's non-homogeneous because of that voltage source that's in there. So once again, the solution to these to this differential equation is going to depend upon the nature of the dampening. Note here also that alpha is equal to R over 2L. In other words, in the series case, alpha, this decay constant, is equal to R over 2L, whether we're talking about the natural response or the step response. That's it for series. And just to review and tie them both together, alpha equaling 1 over 2 RC is the alpha for the parallel. And that's the main difference. In both cases, omega naught is equal to 1 over the square root of L times C. So, we would go through the same type of analysis as we did before, and after all was said and done, we would find that in the overdamped case, where alpha squared minus omega naught squared is greater than 0, that would be overdamped. And V would equal some final voltage, the particular solution, plus the homogeneous solution, A1 e to the S1t plus A2 e to the S2t. Once again, this is just the natural response, or the solution to the homogeneous equation, plus the particular equation, that which is particular to this forcing voltage. And we would have the case where alpha squared minus omega naught squared was less than 0, and it would be underdamped. And V sub c of t would equal V final plus e to the minus alpha t times B1 cosine of omega sub dt plus B2 sine of omega sub dt. Once again, having defined omega sub d to be the square root of omega naught squared minus alpha squared. And that, once again, represents the frequency of oscillation, or the damped frequency, in that underdamped case. And finally, we have the case alpha squared minus omega naught squared equals 0. It's critically damped. And V sub c of t will be of the form V sub f plus d1 t e to the minus alpha t plus d2 e to the minus alpha t. And as was the case in the other circuit, each of the voltages in this circuit, as well as the current, will be of one of these forms, depending upon the relative values of R, L, and C. R over 2L for the alpha, 1 over the square root of LC for omega naught. Thus, S1, S2, omega sub d, or alpha will all be determined by the values of R, L, and C. The coefficients A1 and A2, or B1 and B2, or D1 and D2 are again determined from the initial conditions of the circuit. And this constant, the particular solution, is once again the final value of whatever quantity you're solving for.